We are still doing image-to-image translation, and we are gonna use generative adversarial neural networks for them. We covered one paper, Pics to Pics, which was translating from one image to the other one, and you had pairs of data. You knew that, for instance, this sketch corresponds to this shoe. So you had pairs of data. And then we covered a case when your data could be actually unpaired. You have a data set of images perhaps taken in summer, and you have a data set of images taken in winter. And it could be the case that you don't have pairs of data corresponding to the same scene in summer and winter, because then you need to set up your camera in the same location, make sure everything is controlled, which is not possible. So you have data X, you have data Y. Now you want to do translation, and this is sort of unsupervised. This one is supervised, this one is unsupervised. And because of that, you have a marginal distribution on the X domain. You have a marginal distribution on the Y domain. But what you're interested in is the joint distribution between X and Y, because as soon as you know the joint distribution, you can condition. You can find out what are your conditional distributions. And as soon as you have your conditional distribution, you can condition on this image, and that's going to give you the corresponding image in the Y domain. So what you're truly after is finding the conditional distribution, or actually the joint distribution between X and Y. But there are infinitely many joint distributions whose marginals are going to match with the distribution from the X domain and with the distribution from the Y domain. So this data is definitely not enough, because there are infinitely many of them. Therefore, you have to regularize your problem. You need to start narrowing down your search space for those joint distributions. And that's the idea of UNIT. UNIT stands for Unsupervised Image-to-Image Translation Network. Parts of it we covered last session, but it's actually a good idea to go through them again. As I mentioned, the idea is that you want to learn the joint distribution, but all you have data for are data on the marginal distributions of the X domain and the Y domain. There are infinitely many possibilities. There are infinitely many joint distributions that are going to give you those footprints in the X and Y domain, those marginal distributions. Therefore, you have to make some additional assumptions to narrow down your search space. And the idea here is to use a shared latent space assumption. The idea of the previous paper was cycle consistency. If you take an image, translate it to the other domain, and translate back, it should give you the same image. And we had a similar idea. We didn't cover it, but this is one of the ideas that people use in translation from English to French, back and forth. That's the idea of back translation. You translate from English to French, and then from French to English, you translate back, and then it should give you the same sentence or a similar sentence. That was cycle consistency, or in language, you call it back translation. Here is another idea. What if you have one Z, but two different functions, G1 and G2? These are two different generators. Their input is the same. It's going to take a random variable or random latent vector as its input, and then they're going to output two images. They're going to go, the same Z is going to go through two different networks. And that's going to give you X1 and X2. If we can somehow control E1 and E2 to take two different objects, two different images, X1 and X2, and map it back to Z, to the same Z, then this is called the shared latent space assumption. So there's a shared latent space between X1 domain and X2 domain. We are going to need some neural networks here. To train your generators, you're going to need discriminators. So whenever you have a generator, you're going to have a discriminator. And then you're going to need two encoders to take you from the image domain to the latent space. Let's assume that this is doable, that you have two neural networks operating on two different images, and they're going to give you the same Z. If you take the same Z, push them through two different generators, that's going to give you two generated images. And then it turns out that this assumption, is going to imply cycle consistency. It means that it's a more relaxed framework compared to cycle consistency. There is going to be a larger class of joint distributions that are going to satisfy this compared to cycle consistency. And why is that? The reverse is not true. If something is cycle consistent, or this class is actually bigger than the class of cycle consistent neural networks. And why is this true? If you take E1 and then G2, that's going to give you a function that is going to take you from domain 1 to domain 2. And if you take E2 and G1, that's going to give you a function that's going to take you from X2 to X1. And because Z is the same, these two functions are actually inverses of each other. If you take X1, push it through E1, push it through G2, go back using E2, and then go to the X domain using G1, that's going to give you the same X1. And the same thing is true if you do it the reverse. Up until this point, we covered last session. Any questions? Is everything clear? Okay, perfect. Now it's a matter of training all of these neural networks. You have 6 neural networks that you need to train. Therefore, you need to write down proper loss functions. Let's see what we can do. The first one is going to correspond to this route. So what you're going to be seeing here is going to look complex, but keep referring to this image, and then things are going to become clear. If you take X1, you go to Z, and then come back, that should give you the same image. So it's an encoder-decoder architecture. But at the same time, you want to have some randomness, and you want to work with the stochastic neural networks. The one that is going to take you from the X domain to the Z domain, that's an encoder. Let's make that a stochastic. And then it's going to become variational autoencoders. So this is going to be an autoencoder, and we're going to make it variational autoencoder. But all you are doing is that if I take X1, go to Z, and then come back, it should give me the same image. And the same thing for the other route. If you take E2, come back, it should give you the same image. This E1 here, the neural network over there, is going to be the mean of a normal distribution. So the mean of this random vector here is coming out of your neural network. And the variance, you can just set it to identity. Or you can have another neural network here. But let's simplify things because the method is already complex enough. And this is going to introduce stochasticity. Why? Because you can keep sampling from Z1. Your mean is deterministic, but there is a distribution around your mean. And if you remember, this Q is supposed to approximate your posterior in a variational autoencoder setting. Okay, perfect. Now that you have a stochastic operation in your neural network, you need to somehow backpropagate through it. And we learned how to do that. The idea was to use reparametrization trick. You have Z1 to be the mean plus some random variable that has nothing to do with the parameters of your neural network that you want to learn. So you can basically keep sampling from a Gaussian distribution, and then that's going to give you your Z values that you can push through your generator. So what did we just do? We took X1, we went to the Z domain, that was the mean, we added some noise, and then we are coming back. And this is why you have X1, because this was this image, and you're going from domain 1 to itself. You go from domain 1 to itself in terms of notation, so the notation makes sense. Now we have to train this. We are going to write down our usual variational autoencoder loss. There is going to be some regularization going on. We don't want our variational encoder to deviate too much from a prior assumption that we make. That's why you're going to control the KL divergence between these two. That one is just a regularization term. This other term, you take Z1, and then you're going to use your generator to come to the X domain, to the image domain, and you want to make such data more likely. And then at the same time, you keep sampling from your encoder. So you take X1 through this operation. It's going to give you the mean. You add some noise to it. That's going to give you your Z1. And then you take your Z1, push it through your G network. That's going to give you your image back. And then you want to make that more likely. This is the variational autoencoder loss. We covered it, but it's really intuitive if you think about it. If your probability distribution over the space of images is just normal distribution. This is your likelihood assumption. Let's assume that that's normal. And then the log of a normal distribution. In the normal distribution, you have exponential. The log is going to cancel the exponential term. And then what's going to remain is the mean squared error. That's what's going to remain. In the end, what you're doing is you take x1, you go to the z domain, add noise, come back, and then try to minimize the mean squared error between the prediction and your original image. At the same time, you're regularizing some of your terms. And this is actually going to end up giving you L2 penalty on the complexity of z. It's not going to be on the parameters, it's going to end up being on z. This is a regularization term. This is going to be a usual mean squared error term if you assume Gaussianity here, or normal assumption here. In terms of your prior, this is the prior that you're going to be using to regularize your variational distribution. But you have the flexibility to modify P. It doesn't have to be normal. You can make a Laplace distribution assumption. In the end of the day, even if you don't know what is the formulas for Laplace distribution, it's going to end up giving you absolute distance. Rather than squared distance, you're going to end up with absolute distance. Okay, so far so good. I need to hear a couple of yeses. Okay, perfect. You can do the same thing for the x2 domain. So whatever that's symmetric, I'm not going to cover. That's one loss of the variational autoencoder, which is basically a reconstruction loss. There is this assumption here that was really crucial for you to obtain cycle consistency. And that was the assumption that if you take x1, push it through your encoder. If you take x2, push it through the corresponding encoder, it should give you the same z. This one is a little bit harder to enforce, if at all possible. It is actually possible. We are going to see it in the next paper. But there is going to be some tricks here. And the idea is you're going to have some high-level and low-level features. Now you're modifying the architecture a little bit. What are you doing? Anything that is within this region, I mean, in terms of these arrows, you're going to share them. So this encoder here and this other encoder, they're going to be shared the last few layers, and the first few layers are going to be different. Same thing for your generator. These few layers are going to be shared between your generators, and then they're going to depart. They're going to have different heads. And that's what this weight sharing idea is trying to do. And it's trying to make this hold, which is not going to do it. There is no guarantee that doing so, sharing parameters, is going to satisfy this, but it's actually going to help. Okay, so you're going to do some weight sharing ideas. Now it's a matter of training your generators, because you want to end up with diverse images at the same time. For the first domain, to train your generator, you need a discriminator, and then you're going to have the same thing or a similar thing for the other domain. But here we have to be careful. When you were doing image-to-image translation, you were conditioning on the image from domain 1 and then generating an image in domain 2. So domain 1 was one of your inputs. Here, you can end up with two different generated images based on what you actually input. Let's see, what am I actually talking about? You take x1, using E1, you can go and find your mean, sample around that mean, some z. Now you have two options. Use G1 and come back, or use G2. Or equivalently, you can take x1, using E1, go there, sample, come back, or you can have x2, use E2, sample from your z domain, and then come back using your generator. One of them is taking as input an image from domain 1 and then going back to domain 1. The other one is taking an image from domain 2 and going to domain 1. This one corresponds to the one that takes you from one domain to the other domain. And this is the one that you're going to train it adversarially. This is the one that's going to have a GAN loss. The other one is exactly what you did with your variational autoencoder. And that one we covered. That one had supervision. This one is going to have adversarial training. So we're going to focus on the translation stream. And then you're going to write down your regular GAN loss. You have a discriminator discriminating between images in the x1 domain and the images that are generated from taking this route. You take x2, you go to z, and then go to the x1 domain. And this is the way that you're going to train your generator and discriminator. Okay, so far so good. I need to hear a couple of yeses. Okay, cool. Now let's do cycle consistency loss. Even after weight sharing, even after generative adversarial network training, variational autoencoder, you're still not able to satisfy this constraint. And then you're just going to give up. And then you're going to go back to the cycle consistency, but it's going to have the variational autoencoder style cycle consistency. And you're going to see what I mean. This one needs a little bit more explanation. Don't worry about these KL divergence terms yet. These are just to regularize. But what do we have? You have an image in the first domain. So that's the image that you have. You take it, push it through E1, sample in that space around the mean coming out of E1, and then use your G2 to go to the X2 domain. And this is X1 from 1 to 2. This is this round. You take X1, go to Z, go to X2 domain. Now you're here. Okay, perfect. Now you take X1, 1, 2, this guy, X1, 1, 2, the one that you just generated, and use E2 to go back to the latent space. Now you're here. And then you sample. That's going to give you a Z in this domain. Now you're going to take that Z, push it through G1. This is what this guy is going to do. And then they need to match, because this is very similar to your cycle consistency, but you were sampling. There was some stochasticity. What you did in the end was you took X1, you used E1 to go to the Z domain, you used G2 to go to the X2 domain, you used E2 to go to the latent space, and then you use G1. And then this should give you the same image. If you put the mean squared, if you use the normality assumption, this is going to give you squared distances between these two objects. Or if you use your Laplace distribution, that's going to give you absolute distances between these two, and you want to minimize that. At the same time, you're regularizing. You're still regularizing your Q1, which is similar to what you have here. At the same time, you're going to be regularizing your Q2, which is operating on the Z2 random variables. But then with a minor difference that the images are not real. These are fake images. X1 is real, and whenever you have that arrow, those are fake images. And that one needs to be regularized as well. In the end, this is going to be your entire loss function. There is going to be variational autoencoder loss for the first domain, the corresponding one for the second domain, GAN loss for the first domain, GAN loss for the second domain, and cycle consistency losses for the other domains. And then you can do your translation. How? You take X1, you push it through E1, you're in the Z space, sample around the mean, push it through G2, that's going to give you an image here. Now you translate it from one domain to the other domain, and you get the idea how to go back. E2, G1 is going to give you the next sample in the X1 domain. And these are the type of samples that you're going to get, and they look extremely good. And this is your input space. There is another domain of people having blonde hair. These are different people, so you don't have pairs of data. And then you can turn the hair of this person to be blonde, or you can make somebody to be happy or smiling. Was everything clear? Okay, perfect. It looks complex, the math, but if you want to decode it, understand all of the details, just follow this figure. Maybe 1 month from now, if you forget anything, look at this figure, and then you're going to understand the corresponding loss when you're writing your code. Okay, perfect.